Hoover High School, AP Chemistry. This is Lesson 15, Gas Laws. Okay, so gas laws deal with gases. Gases are molecules that are separated from each other. We generally think that they float. They might actually fall to the surface. But we can think of them as independent. Remember, we said molecules are independent structures. They can move independently. And when they do that, and particularly when they float, they are gases. So these are water molecules in gas form. They're in vapor form. And that occurs when water molecules, if they have low energy, they will stick together because they have a positive and a negative end. And these are like weak magnets that attract each other. And if they have very low energy, those magnets will overwhelm that weak energy and they'll stick together very tightly, and we call that ice. If they have a little bit more energy, they'll stick together, but they'll be able to move around each other while still maintaining contact, and we call that liquid water. That's why water sloshes around. If we give them even more energy, then they can actually break apart from each other and also defy the Earth's gravity and move away from the Earth and basically float into the atmosphere. So if the kinetic energy overwhelms the Coulombic attractions, then the molecules separate and exist as gas or vapor. The word gas has nothing to do with the substance that people buy in gas stations. That's gasoline. That's just simply a name for a chemical compound that's used to fuel cars. It has nothing to do with gas in this sense. So the study of gas laws treats atoms, molecules, or ions in the gas state as though they're little balls. We don't care about protons, about neutrons, about electrons. Since the gas can be either atom, molecule, or ion, we just use a generic term particle. It's just referred to as a gas particle. Gas particles don't randomly change direction. You must imagine that these particles are changing direction because they are encountering other particles that you can't see, or the sides of the container, and this gives gas particles their apparent random motion. So if I had drawn a lot of gas particles there, it would have been a little busy, but that's actually why they're changing directions. They're bouncing into other gas particles. Another reason is if they're being heated up, they'll gain energy, and that can cause them to move upward in kind of a random fashion. And if wind is blowing, then that can cause them to move as well. That's convection, and that can cause the particles to move as well. So gases can take part in chemical reactions. So here's the reaction that creates water. It's two hydrogen gas molecules, two molecules of hydrogen gas, plus one molecule of oxygen gas, produces two molecules of water. Now that water could either be in liquid form or in gas form. The point is, however, that the two gas molecules can create chemical reactions. In fact, gases, because they move at high speeds and smash into each other and break each other apart, they're actually very effective at creating chemical reactions. So in this unit, though, we're only interested in how gas particles behave due to four factors. So pressure, and that's the pressure of the atmosphere in which they're in, that's P. Temperature of the atmosphere, the volume of the container they're in, and the number of particles, and that would be basically number of moles. So pressure is the amount of force per unit area. That's the definition you might have heard in physics. The pressure of a gas can be thought of as the frequency with which the gas molecules hit the side of the container. So the more often the gas particles, I should say, they could be molecules or atoms or ions. The frequency with which the particles hit the side of the container determines the pressure. The more times they hit the container per second, for example, then the higher the pressure is of that gas. The units of measure for gas, the gas law variables are, for temperature, it's Kelvin. Now we also measure temperature more frequently often in centigrade. Centigrade can be converted to Kelvin, and if to use the ideal gas law, which we will learn about in this lesson, you must do that. You must convert centigrade to Kelvin. We'll learn how to do that. Volume in liters. So the volume must be in liters. If you're given a volume in milliliters, which you often are in chemistry, you're going to have to convert that to liters to use the gas law. Moles, that's simply the number of moles. It's a number. It's how many of those 6.022 times 10 to the 23rd baskets of particles that you have. And then pressure has 5 different units of measurement. Its atmospheres is the first one, pascals, kilopascals, that's 1,000 pascals, torr, and millimeters of mercury. So 1 atmosphere is normal air pressure at sea level where we are. So the pressure your body is feeling from the atmosphere is basically 1 atmosphere. Give or take just a fraction of an atmosphere, it's 1 atmosphere. The following are the conversions between the units for pressure. So all of these represent the pressure that you feel on your body here at sea level. 1 atmosphere equals 760 millimeters of mercury, equals 760 torr, equals 101,325 pascals, which equals 101.3 kilopascals. In the same way you made conversions between grams and moles, you can make conversions between any two of the measures above. Why there are 5 different units of pressure is something you don't need to understand. Just know how to convert between them. Okay, we'll just do some sample problems here. So, examples of pressure. How many kilopascals in 2.3 atmospheres? So you identify what you know. You know atmospheres, 2.3, and you're trying to find kilopascals. So you just go ahead and you relate the conversion as being 1 atmosphere equals 101.3 kilopascals. Those are the only 2 you're interested in for this problem. So we start with what we know on the left. You have your conversion factor, 1 atmosphere equals 101.3 kilopascals. You create the ratio that makes atmosphere disappear and kilopascals appear on the top. I don't do the cancellation lines on this, but you can see how atmospheres is going to cancel. So now you do the math, and you get 233 kilopascals. How many millimeters of mercury, and we'll talk about what that means. What does millimeters of mercury mean? In 1.05 atmospheres. So 1.05 atmospheres is going to go over on the left, and you see that 1 atmosphere equals 760 millimeters of mercury. So you create a ratio out of that. You need atmospheres to disappear to cancel out. So you put atmospheres on the bottom, 760 millimeters mercury on the top, and you multiply and you get 798 millimeters of mercury. Okay, and finally, how many torr is 98,600 pascal? So you put that over on the left and you relate torr to pascal. You need pascal to cancel out, so it goes on the bottom, torr goes on the top. You multiply and you get 739 torr. Okay, what is temperature? And one of the things we're going to discuss in this class is the difference between temperature and heat. In common everyday language, people often use them fairly interchangeably. High temperature is the same as heat. But what are they actually? So temperature is the average kinetic energy of the molecules, or really more precisely of the particles. It could be molecules, atoms, or ions. So it's average kinetic energy. Kinetic energy is the amount of energy in a moving object. So a car driving down the street has kinetic energy. If you hold a ball above the ground and hold it still, it doesn't have any kinetic energy because it's not moving. It has potential energy. And if you release the ball and let it fall to the ground, then the potential energy is turned into kinetic energy because it's actually moving. So you may have had examples of that in your physics class. So this translates to meaning that higher temperature increases speed. So if you have a hydrogen molecule there, it's an H2, and it's at a certain temperature, and then you go ahead and heat it up, it's going to move faster. So temperature you can think of in terms of what we're going to be talking about with gases. The higher the temperature, the faster the particle is going to be moving. So let's understand why that is. Okay, so temperature is the average kinetic energy of the gas particles. And from physics, you may have learned this formula. Kinetic energy equals 1/2 mass times velocity squared. M is mass, V is velocity or speed. So by increasing the temperature, you're increasing the average kinetic energy, the KE in that equation. So look at that equation. Since the mass of the particle remains constant, then increasing the KE increases the velocity of the particle. So if KE goes up and mass over on the right-hand side of that equation has to stay the same, that means velocity goes up. So by increasing temperature, you're increasing kinetic energy and therefore velocity. So you can just go ahead and relate that increasing temperature increases the velocity or speed of the particles. Decreasing temperature will slow them down. So let's say we have particles of two different masses in a container at the same temperature. This means that they have the same kinetic energy. If they have the same temperature, the particles have the same kinetic energy. So let's just do a little experiment here. You're not going to have to do one of these problems. The idea is to understand the concept. So the mass of particle A is 2 atomic mass units and particle B is 8 atomic mass units. And let's say that they're at a temperature that gives them 16 joules of energy. So there's the formula. So both particles have the same kinetic energy, 16 joules. So we can compute the velocity of each particle, or at least the relative velocity. So particle A, it has 16 joules of kinetic energy, that's on the left, equals 1/2 times 2, that's its mass, times its velocity squared. Doing the algebra on that, you get a velocity of 4. It doesn't matter what the units of measure are, meters per second, doesn't matter. It's just, we're just going to call it 4, because we're trying to compare it to particle B. So particle B also has 16 joules of kinetic energy, times 1/2, now its mass is bigger, it's 8. And then that's times its velocity squared. So do the algebra on that and solve for V, and you get V equals 2. So the particle that is 4 times more massive only moves at half the speed of the lighter particle. Or you could say it the other way around. The particle that's 1/4 the mass of the larger particle is going to move twice as fast. So the 2 AMU particle moves 2 times faster than the 8 AMU particle. And that makes sense intuitively. A smaller, lighter particle is going to move faster than a bigger particle if you give it the same amount of energy. So the 2 AMU particle moves 2 times faster than the 8 AMU particle. This leads to the following relationship for two gas particles called Graham's law of diffusion. And it says we will define effusion later. Actually, it should say diffusion, but we will define both of them later. Diffusion and effusion are two different things, and we'll talk about them later. So the speed of the lighter particle compared to the speed of the heavier particle, Graham came up with this equation. That if you take the mass of the heavier particle, divide by the mass of the lighter particle, and then take the square root of that number, that will give you the relative speeds. It doesn't tell you exactly how many meters per second they're moving. It just tells you how much faster the lighter particle is moving than the heavier particle. So if we plug the numbers from our last example into that equation, you get 8, that's the heavier particle, over 2, the lighter particle. 8 divided by 2 is 4, and the square root of 4 is 2. And that's what we found in the last example, that the lighter particle was moving twice as fast as the heavier particle. So it gives relative speeds. It doesn't tell you exactly how fast they're moving. Okay, so let's talk about the two temperature scales that we're going to use in this class, the centigrade and the Kelvin scale. The one we use here in the United States for everyday temperature measurements, such as when you want to know how hot it is outside, is the Fahrenheit scale. We don't use that at all in chemistry, so we're not going to talk about it. But we do use these two, the centigrade and the Kelvin scale. So what are they? Well, the centigrade scale is a metric scale. It's the metric system, and it's based around the properties of water. So 0 degrees is defined as the freezing point of water, water being the most common substance on Earth. 100 degrees is defined as the boiling point of water. So below 0, your water's in a solid state. We call it ice. Between 0 and 100 degrees, which is where we are most of the time here in San Diego and pretty much everywhere, is liquid water. and above 100 degrees is going to be gas form of water or vapor. So the centigrade scale is based around this properties of water from 0 to 100. The Kelvin scale is designed with a different purpose. It's designed for scientists. Scientists wanted a scale where 0 really means 0. There's nothing lower than 0 on the Kelvin scale. It is the lowest possible temperature in the universe, and it's called absolute 0. So there are no negative numbers on the Kelvin scale. When you're at 0, you're as low as you can go. And what does that mean? It means there's no kinetic energy in the atom. You've basically taken all the energy out of the atom. The electrons have just collapsed into the nucleus. They no longer have energy. Nothing in the atom has energy. It's basically dead. So that would be 0 K. In laboratory, scientists have come very close to achieving 0 K, but not quite all the way. But within a degree of 0 K, they have come. All right, so absolute 0 is the lowest possible temperature in the universe. It is 0 K on the Kelvin scale. It's negative 273 centigrade on the centigrade scale. A degree on both scales is the same change in kinetic energy. The only difference between the two scales is what each scale defines as 0. So go up there to freezing point, boiling point of water. Notice on the centigrade scale, there's a 100 degree difference between the freezing point and boiling point of water. Go over to the Kelvin scale, and you'll notice there's also a 100 degree difference between the freezing point and boiling point of water. So 1 degree on each scale is exactly the same. It's exactly the same change in kinetic energy. The only thing that differentiates the two scales is what they decide to call 0. Centigrade calls the freezing point of water 0. Kelvin calls the lowest possible temperature you can achieve in the universe as 0. So let's do a few conversions. They're pretty simple. So to convert from Kelvin to centigrade, use the formula Kelvin equals centigrade plus 273. And to go in the other direction, to convert from centigrade to Kelvin, use the formula C equals K minus 273. Okay, so let's do a few examples here. So convert 25 degrees centigrade to Kelvin. So 25 plus 273 equals 298 Kelvin. Just a little detail to know. When you talk about centigrade, you say degrees centigrade. That's that little small circle you see. It's degrees centigrade. But when you talk about Kelvin, you don't say degrees Kelvin. You just say Kelvin. It's not terribly important, but it's just something to know. All right. So convert negative 35 degrees centigrade to Kelvin. So negative 35 plus 273 equals 338 Kelvin. Convert 313 Kelvin to centigrade. So 313 minus 273 equals 40 degrees centigrade. Finally, convert 260 Kelvin to centigrade. So 260 minus 273 equals negative 13 degrees centigrade. It's simple conversion, but you're going to be doing these fairly often when you're doing gas law problems. Okay, now let's talk about volume. Volume is the amount of space an object occupies in 3 dimensions. So in some cases the volume could change. That would be the case of a balloon. In some cases you have what's called a rigid or fixed volume container, such as a glass jar or a metal container of some sort. And the volume would be fixed. It would be constant. Volume is measured in liters. You can think of a 1 liter bottle of water that you get at 7-Eleven. Often in chemistry, volumes are measured in milliliters, and there are 1,000 milliliters in 1 liter. So you're often going to have to make this conversion because the ideal gas law, the volume has to be expressed in liters. So if you're given 467 milliliters, you need to take 467 times 1 liter per 1,000 milliliters. Milliliters cancels out. Liters is the last man standing. And you get 0.467. So you'll be making that conversion fairly often. It's pretty simple. Now there's a special volume relationship between centimeters and liters. 1 cubic centimeter equals 1 milliliter. And that's a conversion that you may be making from time to time as well. Okay, now here's the big gas law that we're dealing with. It's really the single most important law or formula in gas in the gas law. There is one major formula that relates 4 variables of gases. It is the ideal gas law, and it's PV equals nRT. P is pressure, V is volume. That equals number of moles times R, the gas constant, times temperature. R is called the ideal gas constant, and it is that number there. It's 0.0821. And then it has some rather intimidating units of measure: liter, atmospheres over moles, Kelvin. I remember that by just calling it latum over molk. Latum over molk. The purpose of the constant is it cancels the units of measurement, so only the units of the final answer appear. You can think of it as a whole bunch of conversion factors just bundled into one number. So they make everything cancel out that you need to cancel out, except for the units of whatever the final answer you're trying to get. So the ideal gas law is the central formula for the study of gases. An ideal gas is a gas in which the gas particles don't interfere with each other. So we talked about, for example, how water molecules, if they don't have very much energy, can stick together. The positive end sticks to the negative end. They're polar molecules, and so they tend to stick together like magnets. An ideal gas has the gas molecules, the water molecules in this case, would have enough energy that they don't stick together. They just fly around, like we said earlier, like little balls. They just bounce off each other. They bounce off the walls, but they don't get attracted to each other. And that's very important. That's what an ideal gas is. Now, of course, in the real world, not all gases are ideal gases. But at least this allows us to study how gases should behave in ideal conditions. In other words, enough energy so that they don't interfere with each other. And then what you can do is apply that to real world gases. So there's the ideal gas law. So P is pressure, V is volume, N is number of moles, and T is temperature. And those are the units of measure. So notice that pressure's in atmospheres. So if you're given pressure in Pascal, in torr, in millimeter of mercury, in kilopascal, you're going to have to convert it to atmospheres to use this formula. Notice that volume is in liters. So if you're given a volume in milliliters or in cubic centimeters, you're going to have to convert that into liters. N, number of moles, is just a number. And K, temperature, is in Kelvin. So if you're given the temperature in centigrade, you're going to have to convert it to Kelvin. So those are very common mistakes when students start working these problems. They don't convert to the correct units of measure. So these are the units that you have to use in the ideal gas law. Okay, and then there's the ideal gas constant. Think of the gas constant as several conversion factors wrapped into one number. R causes all units to cancel except the one needed in the final answer. So here's an example of that. So there's the ideal gas law. So think of the gas constant as 6 conversion factors wrapped into one number. So here's an example. If you solve for temperature, you would divide both sides by N and R. So you'd have temperature equals PV over NR. So that gas constant R down there on the bottom right side will cause all the units of measure for pressure, volume, and moles to cancel, except the K for Kelvin, which is the unit for temperature. So again, it's like a giant conversion factor with a whole bunch of little conversion factors wrapped into just one number. Okay, now we're going to study relationships between 2 variables at a time. We're going to start with pressure, volume. What happens to pressure when volume is increased? First of all, let's review what pressure means in our context, the way I taught you or told you to think about pressure. It's how many times the particle hits the side of the container. That's the pressure. The more times it hits, the higher the pressure. Volume's very simple. It's the size of the container. And temperature you should think of as the speed of the molecules. You increase temperature, you increase kinetic energy. You increase kinetic energy, you increase the velocity. So increasing temperature increases velocity or speed. Alright, so here we're going to compare the PV on the left-hand side, the ones in red. So just look at it mathematically. If you want N times R times T to stay constant, the black ones are the ones that are going to stay constant. and you increase V, what are you going to have to do to P so that N times R times T stays at the same number? Well, if you increase V, you're going to have to decrease P. So again, you want nRT to stay the same. So if you increase one of those on the left, then you're going to have to decrease the other one. So if N, R, and T remain constant, then as V increases, P decreases because the particle hits the sides fewer times. The relation between pressure and volume is called Boyle's law. That is not at all important. AP's not going to test you on that. I'm not going to test you on that, those names. But it is called Boyle's law. Okay, so let's look at this. Both of these molecules, look at the right side of the equation. They're both at the same temperature. That means they're moving at the same speed. And we're assuming that it's the same number of moles. It's one molecule in this case, in each of those boxes. So what happened is if you took that smaller box on the left and expanded it so it was the size of the bigger box, with two molecules moving the same speed, you'll notice the one on the right in the bigger box hits the sides fewer times because even though it's moving the same speed as the molecule on the left, it has to travel a farther distance to get to the sides. So if you were to just kind of time it or count them, you'll see that the molecule on the right hits the sides fewer times than the molecule on the left, and that's our definition of pressure. How many times does a molecule hit the side? Therefore, the molecule on the right has a lower pressure, the molecule on the left has a higher pressure. Okay, now we're going to examine the relation between pressure and temperature. So what happens to pressure when temperature is increased? So if you look at the equation, you see that they're on opposite sides of the equal sign. So as one of them goes up, if the equation is to remain in balance, equal, then the other one has to go up. And in fact, it's a linear relationship, you see. If you double the temperature in Kelvin, you will be doubling the pressure in atmospheres. So it's a perfect linear relationship. So let's look at this here. So there you have a molecule moving around, and now here's the same molecule over on the right, and now you put some fire under it, you heat it up, you increase the temperature, so now it's going to go a lot faster. Alright, so as you increase temperature, you speed up the molecule, and therefore you see that the molecule on the right is hitting the sides more times per second than the one on the left, and therefore it has higher pressure. So increasing the temperature increases the pressure because the molecules are hitting more times at a higher temperature. So if N, R, and V remain constant, then as temperature increases, pressure increases because the particle hits the sides more times. The relationship between pressure and temperature is called Gay-Lussac's law. All right. Now the relationship between volume and temperature. What happens to volume when temperature is increased? Assume all other variables stay the same. So again, mathematically looking at the equation, you can see that since V and T are on different sides of the equal sign, if one of them goes up, the other one has to go up. And in fact, it's a direct linear relationship again. This whole equation is a linear relationship, meaning if you double the temperature in Kelvin, that's the key, in Kelvin. So you go from 300 Kelvin to 600 Kelvin, you're going to double the volume of that balloon. So it has to be clearly a container that can expand, like a balloon. It can't be a rigid container. All right, so if N, R, and P remain constant, then as T increases, V increases. For the particle to hit the sides the same number of times, that's constant pressure, while moving faster, higher T, the volume must get bigger. This is called Charles' law. So you're going to see each of those two molecules go around, make one full cycle around the balloon, each of their balloons. They touch the sides 4 times every 2 seconds, if you put a watch on that. Okay, 4 times every 2 seconds. That means they have the same pressure. They're touching the side the same number of times. So the pressure's the same. But the one on the right, because it's at higher temperature, is clearly moving faster. So if they're both going to touch the same number of times, but the one on the right is moving faster, you're going to have to put it inside of a bigger volume so that it has a farther distance to travel. So the one on the right, they're both touching the same number of times. That's constant pressure. The one on the right's moving faster. Therefore, it has to be moving through a larger volume in order to be touching the same number of times as the molecule on the left, which is slower. Okay, and one more, and this relates pressure and number of moles when the number of moles is increased, or what happens to pressure when the number of moles is increased. So again, you see that they're on opposite sides of the equal sign. So as one goes up, the other one has to go up, and in fact, again, a linear relationship. So if you have a certain number of a certain pressure with a certain number of moles, and you double the number of moles, you're going to double the pressure. So let's see why that is. If you look at this molecule, okay, so the temperature is the same. So these two molecules are going to be moving the same speed, and that's going around about goes around about once every 4 seconds. So it's touching the walls once per second. So that means it has a certain pressure if it's touching the walls once per second. Now we're going to add a second molecule at the same temperature, and therefore it's going the same speed. But because there's now a second molecule, molecules are now hitting the wall twice as many times, twice as frequently. They're hitting it 2 times every second. So what that means is that as you increase the number of particles, you will increase the pressure simply because you have more particles to hit the walls, and that increases the pressure. That's called Avogadro's law. All right, so this takes care of this particular lesson. It's the first in 2 lessons on gas laws. We'll cover the next one. I'll have that up in the next day or so, probably definitely before you come back to class. All right, so go ahead. There will be an assignment going up on this. You can work on that on Tuesday. I'm going to make both of these, since I didn't have this assignment or instruction up by class on Monday. I'm going to make this due on Thursday. But let's try to keep up with lessons. That's the key thing in this class. Watch the videos, keep up with the lessons. Okay, we'll see you next time.